Welcome back to CS520. In this session I want to talk about the idea of a thin lock, which is really just building your own locking mechanism using a compare and exchange instruction. What's the basic idea here? Basic idea is that if the level of contention you expect for your lock is pretty low, then you might want to use a lightweight locking mechanism rather than using a POSIX mutex. And again, what do I mean by contention? I mean how many threads are actually locking and unlocking that lock. I mean, what's the chances that when you get to the lock you'll have to wait? So if you think the chances are good that when you get to a lock you will obtain it nearly always, then what you might want to do instead of using a POSIX mutex is you might want to just use the compare exchange instruction available on the Intel hardware and then do busy waiting anytime when you can't obtain the lock. And perhaps only call yield if you can't obtain a lock after some number of tries. And by yield I mean, so for instance, pthread yield, which means that the thread who calls it wants to give up running on the processor and let some other thread run. Okay, so we're going to have to think back. The compare exchange is a little bit tricky. This lecture is really just another attempt to illustrate compare exchange through a concrete example. But if you remember, we talked about compare and exchange earlier. In its normal use, it takes a register operand and a memory operand. And it implicitly uses the EAX register. So the compare exchange compares EAX with the memory location. If those values are equal, then it sets the Z flag in the E flags register and stores the register into the memory location. Stores this register into that memory location. However, if the values in EAX and the memory location are not the same, then it clears the 0 flag and it loads the memory location into EAX. And again, what's important to realize is that there's two memory operations here, right? There's the compare, where it's reading the memory operation here to compare it with EAX. And then on either of these two if-else branches, it either stores a value into memory or it reads another value. It reads memory 32 again into EAX. Okay. So in order to use this to build locking mechanism, we need it to be atomic. We need those two memory accesses to be atomic. And to obtain that on the Intel hardware, we have to use this instruction with the lock prefix, which in effect locks the memory bus for the duration of the instruction, allowing these two memory operations to happen as if they were atomic. Okay, so that's our building block. We want to try to implement a locking mechanism. Here's the code that was distributed as thinlock.s. Again, it's when it's called from C code, the C prototype looks something like that, right? It takes the address of a lock, which is simply an integer now. A lock is simply an integer in memory, and as a second parameter it takes the number of times to try to obtain the lock. And the way the function's set up, it's supposed to return 1 if the lock is obtained and 0 otherwise. One other little detail is that this assembly language code only does the locking mechanism because to unlock you simply assign a 0 to the word that is the lock. So that can be done directly, easily enough from C. Again, this is another excuse to look at some Intel assembler. Again, these are all comments. And this is the boilerplate for the beginning of a function. All right, we've got the definition of the function name, and we've got the two instructions that begin every good Intel function, which is to save the frame pointer and establish a new frame pointer. One other thing this code illustrates is the next instruction is the push long of EBX. It's because I'm using EBX, but EBX is callee saved. So since I'm using it, I need to save it, and we'll see at the very bottom when we look at the exit code, you see right before I return, I'll restore EBX's value because the caller expects EBX to still be good when it gets back. The function returns. Again, just to point out again, there's boilerplate code here at the bottom where we restore the frame pointer and then do a return. Alright, so let's go back up into the middle here. What's the first thing we do after this initial code? Well, we move long 8 off the frame pointer into EBX. Again, you should realize that's the first parameter. So in terms of the C prototype, that's the address of the lock. And then the move long a 12 off the frame pointer, again, by the conventions, that's the second parameter. So that's the try count. We put that into ECX. Then we have this loop here where we're going to write this loop right in here where we're going to try to obtain the lock. And the core here is this lock prefix followed by a compare and exchange instruction where we're using register EDX and we're looking into memory where EBX points. Remember, EBX is the address of the lock. So I load up EAX with 0 and I load EDX with 1, and when I check the compare and exchange, remember the compare and exchange, again, it's a little confusing. I find it hard to remember how this works. Compare and exchange, what it does is it compares EAX with the memory location. So it's going to compare EAX, which is 0, with the memory location. So it's checking to see if the lock is unlocked, because 0 means the lock is unlocked. And it jumps on equal, which means, in fact, that's this case here, where EAX was equal to the memory location, the value in the memory location. So if the lock is unlocked, then I can jump down here and exit the loop. Remember, there's also a second operation. So if they're equal, if EAX, which is 0, is equal to the contents of the memory location, that means the lock is unlocked. They're equal. We'll set the Z flag, and we'll store the register given in the instruction into the memory location. So the register given in the instruction was EDX, which has a 1. So we'll, as a side effect of the compare and exchange, we will lock the lock by putting a 1 into it, and we set the Z flag and the E flags register so that when we do a jump equal, it's true, and we exit the lock. We go down here, we have to now put a 1 into EAX, because remember, EAX is the way we return function values. So we put a move long of 1 into EAX, and then we fall out the exit, returning back to the caller, indicating that we got the lock. However, if the compare exchange finds that EAX, which is 0 again, is not equal to what's in memory, in other words, not equal to what's in the lock, then the lock is already locked. Okay, that's the else clause on this instruction here. So we clear the Z flag and we load M32, we load the memory address into EAX. Okay, so the jump equal will not be true, will fall through. We subtract 1 from ECX. ECX again is the count of how many tries we're going to do. Again, we check jump equal because if ECX has been brought down to 0, the Z flag will be set by the subtract instruction, it turns out, so we can do a conditional branch based upon that. So if the subtraction brings ECX down to 0, That means we've exhausted all our tries and we're going to give up. We're going to exit loop, jump to give up, which is put a failure code 0 into EAX and then jump to the exit sequence down here. Okay. However, if we haven't pulled ECX down to 0, then I'm going to jump up and retry the loop. And that's called busy waiting. Just going to keep spinning, hoping to get the lock before I exhaust the number of tries. Okay. So see if you can work through that and see if you can understand the compare and exchange. That's really the point here, is to try to figure out how compare and exchange can work and then how it can be used to do synchronization. What remains to be seen experimentally is whether this is really thin enough. Is this going to be any quicker than calling pthreads mutex lock? That would have to be studied experimentally. Okay, let's stop here.